Here you go. So here's what we have. We have two curves, f of x and g of x. And we're going to bound them a to b. Sorry, the smartboard is still stupid. There we go. It is not. So we're going from a to b. And the question that we have today is, how do you find the area between the two curves? So in the last section, with the use of the integral, we were able to find the area bounded beneath the curve. And its application is endless. There's lots of things we can do with it. But in this situation, how do we find the area between the two curves? And it sounds like it would be really confusing. Turns out it's really not bad at all. But it serves as the basis for which we will then find volume and other calculations. And so all we do is this. We just draw another rectangle. Okay? And the width of the rectangle is dx. Because it has horizontal width. Later on, we're going to draw rectangles the other way. We're going to find vertical width. In this situation, we have a rectangle, and there's a portion of that rectangle that actually represents the distance between f of x and g of x. If you notice, this black rectangle that I draw right here, that's the height of what? G of x. And if I draw the blue rectangle, that's the height of f of x. So what would we do with the blue rectangle and the black rectangle to get the green rectangle, which is the actual height that I want? Subtract the two. Exactly. And so all of a sudden, the area of that one rectangle becomes f of x minus g of x. That's the height, and then dx is the width. And that will give us the area of that rectangle. We're not satisfied with one rectangle. How many rectangles do we want? An infinite. And so we used to have to set up a limit with Riemann sums. Now it's super easy for us. As soon as we want to do an infinite number, all we do is this. So the formula for area bounded between two curves is very simple. Integral a b top minus bottom dx. That's it. Doesn't seem very mathy as a comment I'm getting right now, folks. So we could just go AB f of x minus g of x dx. Is that better? Tomorrow we're going to switch that up just a little bit. We all good? No, that would be on Wednesday and Thursday. I said I need 2 days this week. I am considering going on Wednesday. I just checked in with my friend Braden over there. Say hi, Braden. So I'm thinking going 4th hour and 5th hour. So I'll give you more details later on today. Stop by my room. Okay, find the area bounded between y equals x squared and y equals negative 2x plus 3. over the interval 0 to 1. Okay, so this is a big question that people have. How do we find this area? The first and probably the biggest challenge for you guys is going to be, can we actually see the area at hand? So you have to be able to sketch the graph. What does the graph of x squared look like? Parabola. And then how about negative 2x plus 3? Yeah, it's like a line. It's not even like a line. It is a line, right? Now that I've identified a little bit about what the shape looks like, if I'm going from 0 to 1, I want to identify the top and the bottom. What looks like the top? Yeah, the top is negative 2x plus 3. What's the bottom? X squared, so minus x squared. Now, there's something that we have to be very careful about in this situation here, and that's going to be the bounds of integration. Now, it says that we want to find it from 0 to 1, and so it kind of looks like it's going to be this region right here. But we should really check to see where these intersection points are, okay? So how would we find these points of intersection? Calculator, suppose this was an AP exam question that did not allow you to use your calculator. How you can find the intersection of two equations? Set them equal to each other. Thank you. X squared equals negative 2x plus 3. How are you going to solve that? X squared plus 2x minus 3 is equal to 0. Now what? Factor x plus 3, x minus 1 equals 0. What are my solutions? Good. So I have this coordinate right here, which is positive 1, and this coordinate right here, which is negative 3. Suppose you wanted to find the y values. Plug it in. 1 squared is 1, and negative 3 squared is 9. Is everybody okay with that? Okay. So this is the region that I'm... What's that? You can plug it into either one because they're equal to each other. I chose x squared because I felt that was easier. Are we all on the same page? All right. Now, what you have to understand is that we have x values and we have y values. If you draw a rectangle to represent the height between the two functions, okay, notice that the width of that function is dx, or the width of that rectangle is dx. It has horizontal thickness. If I were to draw it this way, it would have vertical thickness. We would call it dy, or dy-ln. Okay? So we have dx for this width. If you are going to have dx for your width, x tells you that you're going to go x bounds. So negative 3 to positive 1. That would be this area right here. What does the problem say? I want to go from negative 3 all the way over to positive 1, just as I want to go from 0 to 1. And so for 0 to 1, that entire time is negative 2x plus 3 on top the entire time. Yep, is x squared on bottom the entire time. Yep, so in order to find that red area, which looks kind of ridiculous, is really no big deal at all. All we have to do is the top minus the bottom and run an integral dx from 0 to 1. Let's figure it out. is my integral that I set up. What's the antiderivative of negative 2x? Negative x squared. Antiderivative 3. Antiderivative of negative x squared. Works out quite nicely that if we plug in 0, we get 0. If we plug in 1, that'll give us the result. I'm going to write everything in terms of thirds. Is that okay with you? So I see I have thirds at the end. So if I plug in 1, what do you get? Negative 1, right, to start. So we get negative 1 or negative 3/3 plus. Then if you plug in 1 for 3x, you get 3 or 9/3. If you plug in 1 at the end, you get minus 1/3. So I heard Riley speak. So 3 times 1 is 3. That's 9/3. Yep. Okay. We'll try it again. I'm going to plug in 1. I get negative 1 plus 3 minus 1/3. I'm now going to make common denominators. That is the exact area. We okay? All right. So that's the basic example. Let's try 2 more. We'll call her a day and get you your worksheet. Find the area bounded between the curves y equals x squared minus 2x plus 1 and y equals 2x plus 1. Anybody notice anything about the graph x squared minus 2x plus 1? It's a parabola. Isn't x squared minus 2x plus 1 just x minus 1 quantity squared? So it's shifted to the right 1 unit. So if you were to sketch this graph, then that's what you have, right? Y equals 2x plus 1. What shape does that make? It's a line. Coming through 1 with a slope of 2. Good. So just by sketching the graph, you should be able to identify what's one of the points of intersection. Everybody agree that 0, 1 is the point of intersection? How would I find the other point of intersection? Set them equal to each other. X squared minus 2x plus 1 is equal to 2x plus 1. Or x squared minus 4x is equal to 0. Somebody? Factor out the x. We knew the 0. That produces the 0, 1, correct? So this is 4. What's the y value? 9. Yep. So if we draw a rectangle here from top to bottom, which one's on top, the line or the parabola? The line, and the parabola is on the bottom. Notice that the rectangle as we draw it, it has horizontal width. So dx is what we state as the width. So I'll show you as you ask the question. I've chosen to bring this topic up right now to try to help later on. Here's the challenge that if we draw it the other way, and yep, this is what we're going to do tomorrow. So instead of top minus bottom, it becomes right minus left. So which one's on the right? The parabola, right? And which one's on the left? The line. But notice what happens as you continue to draw that. Notice what happens here. What one's on the right? The parabola, what one's on the left? And so that's why we can't draw the rectangle sideways. You have to draw it up and down. Because if I draw it up and down like this, do you guys agree that no matter where I draw it, the lines could be on top and the parabolas could be on bottom? So that needs to happen. If that didn't happen, then we would have to come up with a unique way to work through that. It would be challenging. Nope, 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 nope. It's a vertical rectangle because it's measuring a vertical distance. The width is horizontal. The width is horizontal. Horizontal width. So dx tells me that I'm going to use x units for my bounds. So therefore, I have a very simple integral. The integral from what to what? 0 to 4, because I'm using x values, of the top, 2x plus 1, minus the bottom, dx. I have a negative x squared. I have a 2x minus negative 2x is positive 4x. And I have a 1 minus 1 is 0. So I get negative x squared plus 4x dx. That's super easy, isn't it? Antiderivative of negative x squared. And antiderivative of 4x. Um, yeah, I'm going to write it in terms of thirds. I have negative 64 over 3 plus, as I square 4, I get 16 times 2 is 32, so 96 thirds. Negative 64 thirds plus 96 thirds is 32 thirds. There's nothing that I'm doing in the problem that is really unnecessary. This is all stuff that the AP exam is going to want to see you set up. Okay? All right, flip it over one more problem. One of my favorite problems. Find the area bounded between the curves y equals sine of x and y equals cosine of x over the interval 0 to pi over 4. So it requires that you have a little bit of knowledge about the graphs sine and cosine, but I happen to know that you guys all had college trigonometry last year, right? And I know that you had a phenomenal teacher, and I know that you guys learned it really, really, really well. Would you agree with that statement, Kaylee? Yeah. And this test, graphing sine and cosine, you guys all got like 54 out of 54 on it. So I'm confident that this will be no problem at all. So you tell me something about the sine graph and the cosine graph. Let's start with sine. Waves, sine starts at, okay, and it goes up to, what's the period? 2 pi. Not the same thing. You're a liar. You can stop talking. Yeah, amplitude 1 and goes up to 1, down to negative 1. All right. And it's amazing when you first look at it, you're like, I have no idea what I'm doing, but then now it's all coming back to you like, oh yeah, I remember doing this. I was good at that. So what about the cosine graph? Starts at 1. Yep, starts at the max. Where does it go? Goes down. So let's start at 1. Yep, very good. We call those cofunction identities. You had a sheet on all of those last year. You guys know I'm being sarcastic when I say you remember all your trig. I mean, we're way past the point. I've been teaching this class for 8 years now. I totally know that people don't remember their trig. So I know you remember some basic elements. I know you remember some basic elements, which is good. Good. Proud of you, D. Wyland. Okay. So the question is where is that intersection point? We would hope that it's pi over 4. But what if it's not? Then that really changes our method. So, yeah. Good question. Which one is on top? Right now, the green one is on top, and that's cosine. We graph cosine is the green one, correct? So that one would be on top, whereas the blue one would be on bottom. But it changes throughout the whole thing, right? So we're looking for 0 to pi over 4. Let's first find where they intersect. And so we're going to set sine of x equal to cosine of x. Do you remember how we solved that equation? So oh, come on. What's sine of x divided by cosine of x? How do I solve how do I solve tangent of x equal to 0, equal to 1? So inverse tangent of 1, and I get 45 degrees. 45 degrees is radians is pi over 4. So it looks like the intersection happens right here at pi over 4. So the area that I'm looking to identify is right here. It's between the two curves. Cosine will be on top. So we have an integral from what to what? 0 to pi over 4 of cosine of x minus sine of x dx. Don't forget the dx. What is the antiderivative of cosine? Positive sine. Very good. What is the antiderivative? What's the antiderivative of negative sine? Positive cosine. Now, a lot of times we see that 0, you just kind of disregard it, but that's not what we want to do here. Let's start sine of pi over 4, sine of 45 degrees. Root of 2 over 2. Cosine of pi over 4. Sine of 0. That's 0 degrees, right? Or 0 radians. Is sine the x value or the y value? Sine is the y value. Square root of 2 over 2 plus square root of 2 over 2? Ah! Oh. I used to think that they didn't allow like sharp objects in the classroom to protect like the kids from the teacher. They do protect the teachers from themselves. Like I'd be gouging my eye out right now. Square root of 2 over 2 plus square root of 2 over 2 is not 1. Oh no! Ah! YouTube, I'm having a tough time right now. My students want to do this right now. They want to say square root of 4 over 4 is 2 over 4 is somehow equal to 1, and it's just, ugh. The square root of 2 over 2 plus the square root of 2 over 2 is the square root of 2. Because you have. Yes, they did. Because we're laughing at you. You just got done telling me that you guarantee me that the sine of 0 was 1. So I'm sorry for pointing this out. No, the square root of 2 over 2 plus square root of 2 over 2 is not 1. It is simply just square root of 2. Let me change the problem. What's a over 2 plus a over 2? That's 2a over 2, right? It's just a. Half of an a plus half of an a makes 1 whole a. Half of a root of 2 plus half of a root of 2 makes 1 whole root of 2. It's been a really good time. Tomorrow's going to go awesome. Good job. I'll give you your worksheet live.